The last topic I want to discuss is change of variable. For lack of time, I can't give you all the details, but I hope I will give you sufficient amount and give you references for you to do it. So let us take, for example, you take gx equal to f of x plus t, where t is a fixed number. Then you know that integral over ab g dm1 is the same as integral of f dm1. We have done this, a plus t, b plus t. Okay, so this is on the image. Now this is the same as saying that integral over ab f composed with t dm1 is equal to integral over t of ab f dm1. Okay, so this is the other example which we have already seen is when A is a non-singular matrix or non-singular linear transformation. So A defines a linear transformation Rn to Rn. Okay, and then you saw that Mn of AE, long ago we have seen this, is equal to modulus of determinant of A into Mn of E. Okay, so now chi E of A, chi E composed with A of x is chi E of Ax, and this is equal to 1 if Ax belongs to E or x belongs to A inverse of E, and therefore this is equal to chi of A inverse of E. Okay, and therefore integral over Rn of chi E composed with A dmn is same as, now it's nothing but mn of A inverse of E, which is mod determinant of A inverse times mn of E, which is equal to mod determinant of A inverse integral of chi E dmn over Rn. Okay, so you have that integral over Rn chi E of A, chi E dmn is equal to mod determinant of A into integral chi E composed with A dmn over R. Okay, and using this, of course, you can now proceed for simple functions and then non-negative functions and integrable functions and so on, and we can rewrite the formula. So our aim in this section is in this chapter is to generalize this to arbitrary transformations. Of course, not all arbitrary transformations are possible. So we will see what you have. So the previous one, as I said, so integral Rn of f dmn will be equal to mod determinant of A times integral over Rn f composed with A dmn. So this was how. So we want to generalize this to arbitrary. So let us take t from Rn to Rn mapping. So t of x will be equal to t1 of x, t2 of x, tn of x. Okay, so if t is differentiable, that is each ti is differentiable, then we say t dashed of x is definition matrix dt1 by dx1 at x, dt x1 sorry, and dtn by dx1 at x, and then dt1 by dxn at x and dtn by dxn at x. So this is what we call. And then we say jt at x, this is called the determinant of t prime x. Okay, and that means this is called the Jacobian of t at x. So t is a diffeomorphism if t is a bijection and both t and t inverse are continuously differentiable. So if each ti is c1, that means continuously differentiable, that means the derivative is continuous, then we say the function is continuously differentiable. Okay. So here is the important proposition. So U V bounded open sets of Rn. T U to be a homeomorphism, that means 1 1 on 2 and continuous, which is also a C1 map. That means each Ti is continuously differentiable. Okay. E contained in U, Borel set. Then Mn of T of E is less or equal to integral over E mod Jacobian of T dmn. So if you see in the case of linear transformation, mod the derivative of a linear transformation is the same matrix itself, and you will have mod determinant of A, which is the matrix, which will come out and you get integral mn E. Integral over E dmn is nothing but mn of E. So this is exactly the generalization, only you have now less than or equal to sign because of this. Okay. So this is the proposition from which we will start. The proof of this is somewhat tedious, very technical and very delicate also, and long, and therefore I will omit it. So for a proof, see my book which we are following, Measure and Integration. From 77. Okay, so you can see a full proof of this inequality there. So okay, so now we will draw some consequences from this particular result. So this is, I will call this star, which is an important inequality. So U and V bounded open sets in Rn. T U to V homeomorphism and C1 map. E contained in U Borel set, Mn of E equal to 0 implies Te is also Borel and Mn of T equal to 0. Now if T is a C1 map. If the homeomorphism, we have already seen that T is Borel if and only if E is Borel and so on. And here what we are saying is if it's of measure 0, then the image also has to be of measure 0 coming from, so proof U star. Because if E has measure 0, then this integral is 0 and Mn of Te is therefore 0. Okay, so that is the corollary which you have here. Okay. Next proposition. UV bounded open sets of Rn, T from U onto V is a homeomorphism and C1 map. F V to R non-negative Borel measurable function. Then integral over V F dmn is less than or equal to integral over U F composed with the mod jt dmn. Okay, so F composed with T at x, you know, is F of T of x. Okay, so this is the so we'll call this double star. Okay, so let F, so proof F contained in V Borel set. Okay, then F will be equal to TE E Borel, E contained in U. Then chi E we have just seen is nothing but chi F composed with T, because chi F of Tx, that means Tx belongs to F, that means x belongs to E, so that means chi E is equal to chi F composed with T. And then set F equal to chi F E. Then double star is the same as star applied to F. We have F of E, Mn of E is less than or equal to Mn of T is less than integral Jt of E Mn. Okay, so this is exactly the relationship which we have here. So F is equal to chi of E, and therefore this is and then F composed with T. So not no, sorry. This is applied to chi of F. Chi of F. So applied to chi of F. So then you have Mn of F, which is Mn of T of E, is less than or equal to F composed T, which is chi of E, so integral over E, and then mod Jt dmn. So double star is the same as star applied to chi of F. Okay, so now true for simple Borel measurable functions. Then by monotone convergence theorem, true for non-negative Borel measurable functions. This is just linearity of the integral, and therefore this is true. So next proposition, U V bounded open sets in Rn, T U to V diffeomorphism. That means it's a homeomorphism, and T inverse are both C1 maps. Okay, so this is a diffeomorphism. F greater or equal to 0, Borel measurable function. Then integral f dmn over v is the same as integral over u f composed with t mod jt dmn. So this is the change of variable formula. So you want to integrate f over v, and then u to v there's a change of variable, namely a tx. So t of x equals y, and therefore you have f of t of x, that is f of y is f of t of x, and then mod jt dmn. Okay, so you have to, this is just like the change of, this is called the change of variable formula. So okay, so now proof. Well, we already know that integral v f dmn is less than or equal to integral over u f composed with t mod jt dmn. This is double star which you already have. Okay, so I am just recalling it here. Now apply this to T inverse from v to u. Okay, and the function f composed with t mod jt. So what do you get? So you put y equals t of x, x is in u, y is in. Okay, so you have that integral over u, f composed with t at x mod jtx dmnx, of course, is less than or equal to integral over v, because now t inverse of u is v. Okay, so you have f composed with t inverse, okay, mod jt at t inverse y, okay, and then you have mod jt inverse, the Jacobian of the mapping y dmn y. But what is that equal to? That's same as f of t inverse t is just, so f of y mod jt of t inverse y, and j of t inverse y is 1 by jt dmny. But this is equal to 1 because t and t inverse have Jacobians which are the inverses of each other because of the chain rule. Okay, and therefore this is equal to 1, and consequently this is equal to integral v fy dmny. Therefore integral, so we have both inequalities, so this implies double star. So where we are using jt of t inverse of y into, so determinant on determinant again, so let me write not modulus. Yeah, that's fine. Okay, this into mod jt inverse y is equal to 1. Okay, so that proves the result. So corollary, you have UV bounded open sets of Rn, T from U to V diffeomorphism, E contained in U Borel, then you have Mn of T equals integral of E mod Jt dmn. Because we are applying, so apply above result to chi of t. Okay, apply the result. So we have already done that. So you have this corollary. There's nothing to